Hi everyone, we are Andrés Adam, Oriol Crespo, and Joan Pallejà, and we are doing a Convergent Divergent Nozzle application as our Matlab project. So the purpose of this project is the typical case of a Convergent Divergent nozzle with a gas with no chemical reactions inside it. As inputs, we also usually give stagnation pressure, temperature, and density. The velocity we suppose 0, and then the Mach is also 0. We calculate the properties P, T, pressure, temperature, density, and the Mach at the exit. The area 2 is also input, which is very important with the throat area. As we suppose no friction at the walls, it's okay to suppose isentropic flow with properties constant along the section with velocity normal to the section. The isentropic flow has these typical equations which lead to the area relation equation that give two solutions for a given area relation, the subsonic solution and the supersonic solution. We also find normal shock wave at the divergent part of the nozzle. The equations are very important, the Mach and the pressure relation. The normal shock wave, remember that the flow goes from supersonic to subsonic all of a sudden, and the stagnation pressure changes, but not the stagnation temperature. The regimes that we can find at a convergent divergent nozzle depend on the area relation and the pressure relation. The first of all is subsonic. There's no sonic conditions at the throat. The second one is a limit case, subsonic, with Mach equals 1 at the throat. Then we have shock wave at some point of the divergent part that we have to find it. Shock wave just at the exit, this is a limit case, and then we have no longer the exit pressure that equals the ambient pressure, so overexpanded, there's no shock wave that can adjust the flow. The adapted, they are equal, the isentropic expansion leads to the ambient pressure, and subexpanded where the ambient pressure is too low and the nozzle is no longer affected by the ambient pressure. So finding the shock wave is maybe the most complicated process of the program. We have the first area relation, which is this part with this equation. We then have the normal shock wave equation with this red step, and the area relation is between two normal sections. The condition to the problem is that the exit pressure must be equal to the ambient pressure. The procedure then is that we give the inputs, we find the regime, calculating the limit cases, the subsonic isentropic solution, the supersonic isentropic solution, and the shock wave just at the exit. Then if necessary, we find the shock wave and where the flux detachment is. So where the pressure is equals to 0.4 the ambient pressure, and then we calculate the exit parameters that we want.
Our program works using a main function that, given the input parameters, it will evaluate all the procedures to have these different outlet parameters. In the beginning, it have to make this function choked that begins telling that the regime is subsonic and computing the different procedures with the equation that we have explained in the theory part. And then if it says that it's not subsonic, it considers the other different regimes. With this regime, once it's selected, it goes to the main function, and then if it's a shock wave, it goes to calculate the shockwave area. To calculate the shockwave area, we have to make that the pressure at the exit, which is pressure A, it's equal to the P2, that is the ambient pressure. To know the exactly out pressure, we need the MAC at the exit that we can evaluate using the area relation. Once this is made, we can compute the pressure at the exit and then making with this solve know which area we have the shock wave. This is for shock wave and shock wave at the end. In overexpanded, we have a different procedure. We go to this function called release, and in the case of overexpanded, we can plot where it's made. Once we have the area of the shock wave of the overexpanded, that is where the fluxes releases, we go to plot shock. These are the functions that are called, and it gives, given the area, for example, here in a shock wave case, we see that here we have the shock wave in a circular nozzle. We calculate the E of the shock wave, and then with this E of the shock wave, we know in which position it's the shock wave done. If it's not an exact position, we have to make an interpolation that it's here evaluated, and then we plot the position of the shock wave. Then at the end, in the main function, as I said before, we have the position and then the exit parameters here: the pressure, MAC, and temperature. Then how shall we know that this program is working okay? Well, we have some experiments. For example, with this nozzle, we evaluate the shockwave position versus the pressure relation. When it's near H1, not exactly 1, because at exactly 1 there's no flux in the nozzle. When it's near 1, the shockwave that is given very near to the throat, because we will have to do it before to can reach the ambient pressure at the end, and then it goes to the exit when the pressure is the inlet pressure is lower than the exit one. After that, with this other nozzle, we evaluate the MAC versus ambient pressure and the out pressure versus the ambient pressure. And in this case, we can see that at very low ambient pressures, we are in the case of overexpanded. We have supersonic MAC and exit pressure different to the ambient pressure. Then, when we have here shock waves, we see that the MAC is subsonic and that the exit pressure is the same as the ambient. And then in subsonic case, we also have a MAC lower than 1 and the same pressure. These graphs really seems to be right, because it accomplishes the needs of the theoretical part.
In order to simplify the data introduction process, a graphical user interface has been designed. It includes a two-dimensional representation of the nozzle, a data entry section, and a data output section. In the representation, we can see if a shock wave appears, where it will be, and when it will appear, and we can see it graphically. In the data input section, data can be introduced in a TXT file. This data can be the nozzle geometry and the state variables of the problem. In the output section, the solution of the problem is presented. The solution can be presented in two different ways. First, data can be seen in the graphical interface, as we can see. And secondly, data can be stored in a log. Also, the file can be saved with another name or format, or autosaved. Finally, I will show you an example of the input and output files that can be used. For example, here we can see the state variables, how they have to be introduced in this order. Secondly, here we can see the nozzle geometry. The program automatically computes the inlet area, the outlet area, and the throat area. Finally, we can see the output file. Here it's named log.txt, which is the basic name, and we can see, well, all the solution of the problem: the state variables, the basic geometric constraints, an explanation of what has happened, and the geometry that has been used to compute it. Thanks for watching this video, and we hope that you have liked it.